we are live. Welcome to week 7 of the fabulous CSI 45 class. So first on our agenda, we're going to go over the midterm, and then we will learn about classes, how to do classes in assembly. But wait, there's no types. I know. And then we'll learn some new architecture if we have time. Alright, so first of all, let's see how you guys did on the midterm. So let's see. Practice midterm 1, spring 2021. Quiz statistics. So looks like you guys did pretty well overall. 90 to 100%, so yeah, pretty good. See if any of these are tricky. So you guys got the caching thing correct by and large. This one, some of you guys had trouble with. I went through it. There was a typo early on in the midterm before I fixed it, and I looked to see if anybody had typed in the alternative right answer, and it gave points on those. So it's better than 58%. They got this one correct. But yeah, if you have an array that's this big, you got 10 planes, 4 rows, and 20 columns, then every time you go down a plane, you're moving 80 elements to the right. You know what I mean? And I made all of the elements chars, so it's just 1 to 1. I was thinking about making it ints. Maybe I'll do that on the next midterm. Just add some extra difficulty to it. So if the start of the array is at address 6000, if the base is 6000, and you go down 1 plane, you've moved 80 bytes to the right. So 1 plane down would be 6080, 2 planes down would be 6160, 6240. Okay. And so 4 planes down would be 6320. Okay. And then 2 rows down, every row is 20 elements. So every time you go down a row, it's 20 bytes to the right. So was it 6320 plus 40 is 6360, and then 1 more element to the right past that, because it's 1 column to the right, is 6361. It's always good, I think, to think about it logically and just kind of work it out rather than trying to memorize the formula. At least that's how my brain works. I don't, you just kind of think about it logically. You can usually figure these things out. Plain English, what is this code doing? It is writing an int to the memory at address R8 plus R9. Some of you said it's a char. Not a char. If it was a char, it'd be store byte. strb is store byte. This is str, not strb. So, my head's burning. So it is storing an int, not a byte. And then here we've got some bitwise operations that you guys did really well on. Let me pause the recording really fast. Okay. So I understand this one, number 8. Which one's number 8? See, it doesn't actually show me numbers in professor view. I don't know why. It shows it for students, but for me, I have to like the bitwise not. Okay. So you bit twiddle the bits here. So when you bitwise not this, it becomes 0001. Yeah, so Dolio, when you took it, there were 2 different, there was a duplicate. Canvas does that sometimes. So you were supposed to just guess which one was correct. I'll fix it for you. I once saw Canvas put in like 7 duplicate entries, and a student got it right. I was like, how the hell did you do that? It's amazing. Alright, so you need to change 1 line to make this code work right. Pick the modified line. Alright. So the problem here is that we're using branch with link instead of branch. A very common mistake that people make. That's a function call. It's going to mess with your return address and all this other stuff. Use branch always instead of branch. And this was also, I also put this in here so you guys would have an example of a range-based for loop, because that was part of the coding assignment. And then it is doing signed division by 4, not unsigned. Right. Some people said division by 2. No. When you bit shift 2 bits, each time you shift 1 to the right, you divide by 2, right? Because the 4-bit becomes a 2-bit. And if you do 2 bit shifts to the right, the 4 becomes a 1, right? So it's division by 4. Yeah. Parse 2. Is there a typo in there with BGT? Loop stops when. Yeah, maybe, but it's not an option, so who cares? Okay, so that was the midterm. The coding assignments. Let's see. You guys have any questions about the coding assignments? Basically, for the free coding part, you had to write a range-based for loop, and for the other part, there's just a couple pretty easy bugs, like almost everybody got it. So, if you have any questions about it, please ask. Basically, the code that just showed you there a second ago with a range-based for loop was more or less what you needed to do. The last part tricky with Fibonacci. Yeah, the only tricky part with it was that you have to grab previous elements from the array and then write. So you grab 2 to the left and then write to the right. Basically. You see my version of B. Yes, but I'm not going to record this in case I use it in later years. Yeah, so when you load from a integer array, every int is 4 bytes away from the one previous to it, so you have to add 4 to it over and over again. LSL is still 1 stroke count. Yeah, if you just have a line of code that's like LSL, R0, 2, that's 1 stroke count. But you could bake it in. All right, you can do add R0, R1, logical shift left 2, something like that. And so that's free if you do it that way. But if you give just an explicit LSL command, that is going to eat up a cycle. Okay. So there are ways of getting the logical shift lefts for free. The way I did it, but if I had, looked at the documentation, I could have used the exclamation mark when doing memory address to do a write back. So what you can do is you can put an exclamation mark and it'll both read from a pointer and advance the pointer to the next element, which is, it'll save you an add. Like, rather than having to add, 4 to the pointer every time you read an int and then add 4 to it. If you use the exclamation mark, you can get that add for free. But there was no speed component on the midterm, so I didn't care. It would involve me having to reach over there and grab the book. All right, so let's learn about classes today. So some of my students have gone to Santa Cruz, and at Santa Cruz apparently they do data structures in C, which sounds rather mean to me. I don't know. Sounds kind of odd, because C++ really is better at doing data structures than C, because we have the public and private. With C, everything's public, and you don't have any member functions. And so let's actually take a look at that. So let's do a linked list in C. Then linked list.c. So. And none of this is going to exist, right? I'm not getting these cool things. Stdio.h. There's no namespaces. Yeah, C++ is 1 better than C, right? That's the plus is for. So let's see. Let's see. How do we want to use this? We want to do something like list L, which is going to look like a lowercase. No. Yeah. List. Not a fan. Whatever. Okay. And then we want to do something like list dot push back. Princess Peach. I don't know. Maybe we're making a list of all of the people in a Mario Kart game. Okay. List dot push back Bowser, Mario, etc. Okay. Trouble is there's no member functions in C, right? Can't do that. So sucks to be you. So instead, what you have to do is make a global function called like list pushback, like that. And so struct, and see, it's like typedef struct. Such a weird syntax. C++ does the typedef for you. Typedef C struct. Such a stupid syntax. Yeah. Typedef struct books book. Yeah. It's like that. So if you don't do this, then you would have to say struct list every time you make a list. And so it's typical that you typedef struct list underscore list to be list. And then that allows you to use it this way. And our list is going to have, because there is no, it's a struct, there's no privacy, everything's public. You're going to have a char star called data. Let's not use. Okay. And we're going to have a list pointer next and a list pointer previous. Do doubly linked list. And then we can have a function called list underscore pushback, just in global space, taking in a char star string. And yeah, and then we're going to need to take in a list also, aren't we? And everything, there is no call by reference, so if we want to modify the list, we got to pass it as a pointer. So in C only has call by value and call by pointer. Don't have call by reference. So C strings are super duper annoying. So I'm actually going to start by not doing that. Or start by just doing ints. Then we'll add complexity later. So So notice there's no constructors either. So if we just call pushback on these things without initializing the list, head and tail are all going to have uninitialized data. So is list an array type deal or a linked list? Well, so who knows? If you implement an ADT properly, a list just means it's a list. You can add elements to it, to the front, to the back, whatever. No random access. There's a list interface, and pushback pushes the end of the array, pop from the front. It's it may be an array. In this case, it's not an array. It's just a bunch of pointers. Okay, so can you dereference with star? Yeah. The reference and dereference operators star and ampersand work the same way, and that's where call by reference came from, right? That's why there is call by reference in C++, is because that's the referencing operator, and it takes the pointer to something, and it just does that for you automatically. So when you do call by reference like that, then what it does is it takes the pointer to list, and then dereferences it. But we don't have that, so we need to have a pointer to a list in order to modify it. So in C, you will see this over and over again. In C, you will see everything passed by reference, by putting a reference in front of it. And a lot of C people like it this way because you can tell that it's going to get modified, right? When you do the function call, that's where you put the ampersand rather than in the function, so that you know when something is going to get duplicated and when something is going to get passed by pointer, right? And there is something to that. You know, C++ will hide a lot of logic, and C people, everything's explicit. There's no constructors that secretly run. There's no destructors that secretly run. There's no copy constructors that secretly run. You know, you do it all yourself. You get used to it. So, how does it know that node has a list? It doesn't, but list has a node. Right? So we need to initialize these things, right? All these things need to be initialized, right? And so we have to make a global function for that. So we have to make a global function, and this is void. We need to make a global function called list init, taking in a list by pointer. And so this is our constructor, right, in C. So list points to head equals list points to tail equals 0. This is null, i.e. null pointer. Yeah. Size equals 0 as well. Okay. And so this is going to initialize our pointers to be null, our size to be null. We can do a node init, void node init, passing in a node by pointer. And we'll do the same thing here. Node points to next equals node points to previous equals 0. Data equals 0. Okay. And so if you're going to be like, wait, isn't the global namespace going to be like polluted by all these different function names? The answer is yes. Yes, it is. And so it's very common for people to put prefixes into the function name itself. This has the effect of a namespace or a member function, right? If you look at the GNU multi-precision library, which good manufacturing practices, which we used in C-Site 26, GMP lib. It's in C. And where is the documentation? So let's just look at random number functions, seeding. You see how all these functions have GMP underscore at the beginning of them, right? That's essentially how they do a namespace. So as long as you don't name your functions with GDB at the beginning of GMP at the beginning of them, then you'll be fine. And so the C world isn't like unsophisticated world. It's a sophisticated world that has its own idioms, its own practices, and they have the same problems that we have in C. It's just they kind of handle it differently. Everything's very upfront and explicit. That's why C is actually more popular than C++, believe it or not. There's more people programming in C right now than C++. Is null pointer defined in C? I don't believe so. We can find out. Actually, let me see if this will compile. I've been typing a lot of things, and I don't actually know where I'm at. I should probably call list init, huh? List init, passing in list by reference, effectively. And then play pushback. Pushback currently does nothing. Okay, let's see if this gcc ll.c unknown type name list. Right. That would be a node, would it not be? And it might have to be underscore, huh? Yeah, because we haven't finished the type def yet. There we go. So stupid. Unknown type of name underscore node. Right. Struct underscore node. Yay. Data undeclared, first used in this function. Right. The node points to data. Size is undeclared. Same thing here. Right. This points to size. All right. I really need to get COC installed on this. All right. So let's see if null pointer is declared. I'm reasonably certain it's not, but nope. Null is. So null is 0. It's just an alias for 0. Pretty much everything in C is an int, you know. So pointers are ints. Everything's an int. All right. Why do you need the underscore at the beginning of the type def and not after the ending bracket? What I'm doing is, so if I don't do this, like if I don't do the type def thing, like that, then every time I refer to a node, it will be a struct underscore node, like that. This is the way that C refers to variables of struct types. You have to say struct every single bloody time, and it's super irritating. And so C++ will do the type def for you. When you say class list, it creates a new type called list. In C, it is of type struct node. And so every time you refer to it, it is struct node, struct underscore node. And so the idiom that we use in C is we type def it. And so what this is doing is it is type defing basically everything from like here to here, if that makes sense. It's type defing all of this stuff to be a new type called node. And so we can't refer to it here because it doesn't exist yet. Yep. So a type def is a type alias, right? It's just, it just allows us to not have to write struct node every time. Bleh. Right. So definitely 1 point in C++'s favor there. It's kind of irritating to do that. So that seems fine to me. Okay. All right. So the code's compiling, and now we need to write a list pushback. So let's see this. While true. And if you're wondering, does while true exist? Does for loops exist? Yeah. Yep. Not range-based for loops, but regular for loops, yes. So pretty much everything. If statements, for loops, all your basic types, int, float, double, all those things exist, except C does not have range-based for loops. It's called the ternary operator. Doesn't have call by reference. Let's see. Does not have classes or private or public or member functions. It only has member variables. C does not have call by reference. Only call by pointer, which does the same thing, or call by value. C's standard library is smaller, obviously. It's pods all the way. Okay, so all right. So while true, okay. So how do we do I/O? I/O in C is via printf, scanf, fprintf for files, and fscanf for files, sprintf for strings instead of a string stream. Yeah, so all the same functionalities there. A lot of people actually prefer printf, print function, better than cout because it's a little bit more condensed. The trouble with printf is that it doesn't do type checking. So printf, please enter an integer to add to the list. You have entered %I so far. So this is a print function. Print function takes a string and a variable number of parameters after it. And the number of parameters after the string is based on how many of these special format characters that you have in the string. And so C++ has recently adopted C++ 20, very recently actually, and still I don't think it's rolled out yet, has adopted something very similar to this. But the problem with this code here is that this code is undefined behavior. The reason for that is because it is going to be expecting me to pass in an integer here, and I'm not. And so it's probably going to explode. Let's try this out. While true, jeez, yeah, you don't have true either. So how do you do constants in C++? Hashtag define true to be 1. Hashtag define false to be 0. So this is how you do constants in C. Okay. And yeah, didn't crash. Good on you. But this is undefined behavior, and the reason for this is because it is going to be reading from what is it printing? You have entered 0 so far. Interesting. So it's reading from some random chunk of memory, this thing, and that's a very kind of dangerous thing, and it doesn't actually come up as often as you'd think. But you need to pass in a parameter, one parameter for each of these formatting things here. And you can look up the documentation on the formatting, is it man3 format? So there's all sorts of things you can put into these format commands here. Decimals, precision, and just all sorts of interesting things. And so the documentation on printf, these are all the different things you can pass in there. I is for an integer, and then F is for a double, not a float. Signed, unsigned, all these kinds of things. So we need to make an integer count equals 0. Let's do that. So now it's going to count how many times we have entered something to the list. So how do we read? How do we read something? So in the original C, you couldn't even do this. In original C, all of your variables had to be declared at the top of the function. Later on, they made it a little bit more C++-like, where you could actually make a variable down below. Let's see if this will work, actually. Int temp 0. Let's see if that works. Yeah, that works fine. Yeah, originally in C, this would actually not be legal. You would have to, maybe at the top of the scope, but your variables had to be at the top of the scope. You couldn't actually do this. And yeah, they got rid of that for good reasons. So how do we read a variable from the keyboard? We use scanf. So scanf looks like this, and there is a bug here. Okay. So this is going to read an integer from the keyboard and put it into temp, or will it? Let's find out. Do C structs require a semicolon after the definition? They do. That's why C++ does it. Segfault. Really? There we go. Segfault. Thank you. Jumped the gun on that one. So scanf actually requires this parameter to be passed by reference, by pointer. And so I did not pass it by pointer. I passed the value of temp. This is called by value. I am passing 0 as my memory address. And so it tries to write the value of this to the memory address passed in here, 0, and it segfaults. So you need to put an ampersand there. Remember, anytime you pass something by reference in C, you do it like that. You put the reference right there, front and center. A lot of people forget that. A lot of people segfault their code that way. Briefly, people fix it pretty quickly. Do C structs require a semicolon? Yeah. So if I were to just make a struct Bob, this would be the syntax. Okay. And then I could refer to it down below as struct Bob temp, something like that. Okay. So that's there because this is actually the same thing as this. So this makes a variable of type struct Bob. This makes a variable of type struct Bob. Both of them are named temp. They're actually doing the same thing, except this is also declaring what's in it. It's got int A and B, like that. So if rather than having to do two separate things, you could just combine them together like that. But every time you refer to struct Bob, you would say struct Bob, struct Bob, struct Bob, and it's super annoying. So we typically do the typedef approach like this, which gets rid of the semicolon is actually for the typedef, right? And so again, this is like it's like this is the command, right? So this is actually not a variable of type node. This is actually the second part of typedef. But when you add typedef, doesn't it make an object? Nope. This is actually not an object. This is like I said. This is the second part of the typedef, right? The syntax for typedef looks like this: typedef int Bob, and then you can make variables of type Bob like that. Okay. And so the first parameter to typedef here is this. Is that. So it's creating all that highlighted stuff there is, that. So yeah, so that's, yeah. Mm-hmm. Okay, so that is going to read in an integer. Now we need to do list push back, passing in the list by reference and pushing in temp. And so this is going to add to our linked list. Now you might be like, wait, what's stopping us from just calling like node, something or other? Nothing, right? Nothing. There's no privacy. There's nothing stopping you. You just have to know. You have to remember to call init. Like if you want to if you have a constructor, you have to call the constructor manually every time. If you forget, you're going to get undefined behavior. So in C++, you'd have a constructor here that would initialize all the values to be null, etc., etc. Nope, not in C. In C, you got to call it yourself. And GMP does it the same way. You have to call init every time you got a struct. You make a struct, you call init on it. That's just how it is. Okay, so here we are going to add a number to a linked list. So the first thing we need to do, you tell me, what is the first thing you need to do when working with pointers? Well, you just heard my linked list lecture for the past 2 weeks. For this function here. Yeah, we're not going to initialize it. The first thing we do here is what? If list. If list. Yes, very good. So, if list. Good. Or alternatively, if not list. All right. So, if not list, we just return, or we, I don't know, die or something. Or another way we could do this is say assert list. Hashtag include assert.h. Okay, and so what this will do is say, make sure that list is not null. If it's null, die. Okay. So if I were to call list pointer Bob, and I'm going to call list push back, passing in Bob and 42. When I run it, I get an assertion failed. List push back, assertion list failed, abort. Okay. So if you ever seen assertion failed errors in Bethesda games, a lot of times they'll actually just do something like this in their games. They'll just be like assert 0, and then you'll get this fantastic error message: assertion 0 failed, which tells you absolutely nothing about the code. That you put this in there to be like, if we ever get here, die, and it gives you absolutely no information whatsoever on what the actual problem was. Well done, Bethesda. And see rl includes.h. Yes. It used to be that way in C++ too. C++ eventually standardized on not having .h files for the system header files. When people make header files, they're still .h or .hpp files for C++ headers, which never really caught on too much. But for the system headers, they dropped the .h. The reason for that was because they wanted to differentiate between assert and all the C stuff got put into header files that this and this are the same thing in C++. But they're not. They're not, because this is the modern C++ version of this. The only difference is it puts everything into the std namespace. So if you include iostream.h, then that actually does not put cout and cn into the std namespace. That still works for backwards compatibility. So, and then anything that was in the C library got tagged with a C at the beginning of it. So you have include CC type, include CMath. All those things are from the C standard library. And so they did that to sort of differentiate between the C standard library and the C++ standard library. Anything in the C standard library that you do C std.io, then that gets wrapped into the std namespace so that it doesn't pollute the global namespace. C++ has been moving a lot in the direction of not having random names and symbols in the global namespace. So that's the difference there. Std assert 0 in C++. That is correct. Yeah. All right. So yeah. So check to make sure it's null. Not null. Let's get rid of you. Okay. So okay, we now know that list is not null once we get past this point. So we can say now we need to see what. So we know the list is valid that we've passed in. That's not something you have to worry about in C++, right? If you call a member function on something, it exists, right? Unless you did something really weird. So what's the next thing we need to check? There's more pointers that could be null. So we know the list is not null. What else could be null? So thing.h doesn't put it in std, but thing does. That is correct. But and it'd be C thing. If it was part of the C, if it was part of the C library and it was called thing.h in C, in C++, modern C++, it would be called C thing, and all of it would be wrapped in the standard namespace. But you could still use the old term as well. And all of the C++ header files are all in std now. The next pointer. We don't have a next pointer yet. We're just in a list. We don't have a node yet. That data is valid? No. We can take any int, I think. Okay. Head and tail, a very good vector. So we need to say if list dot head is null, or list dot tail is null, then we have an empty list. Or we can check to see if size is 0 as well. So, but it's always a good idea to check to make sure your pointers aren't null. Every time you work with a pointer, first make sure it is not null. So if head is null or tail is null, that means we got no list. And so list points to head is equal to list points to tail. We're both going to set them. And we are going to malloc. We are going to new some memory. So we are going to make a list pointer. That's a cast. That's a C-style cast. We're going to malloc. How much memory do we need to malloc? 50? 60? How many bytes? How many bytes do we need to allocate? That is correct. Size of list. Parentheses all match up. Okay. So that is going to new. This is the C version of new. And the way that it works is malloc, memory allocate, just takes in a number of bytes. And the number of bytes it takes is how much memory you're going to get. Okay. So it's a very simplistic system. You can malloc 10, and it will give you a pointer, and it returns a void pointer, because C doesn't have the same strong typing guarantees that C++ has. Malloc actually will return a void pointer. A void pointer is an untyped pointer. And so you have to cast it to a whatever thing you have. Incompatible, implicit. We need stdlib. Okay. So that'll actually work, but it's in general considered bad practice to do it this way. You want to make it a list pointer, and so this is the pattern you'll see over and over again with malloc, which is you get a number of bytes, and the number of bytes is usually computed using size of. Size of is a intrinsic. It's not actually a function call. It's actually part of the language that will compute how many bytes this bad boy over here is. And so you don't have to sit there and count on your fingers and toes. And as you move between architectures, these things will change in size as well. You don't have to worry about that. Size of will do it for you. And it's not actually a function call. It'll compile down to a number. Like in this case, 12 maybe, probably. I don't know. And then it converts it to a list pointer. Again, this isn't exactly necessary, but it's a good practice to follow. And then it stores that memory address into the head and the tail. So the head and the tail are now pointing at a new chunk of memory. Are we done? No. Because there's no constructors. Remember? There's no constructors in C. And so now we need to initialize this person. New calls the constructor, right? That's why we don't use malloc in C++. So we need to call node init, passing in list points to head by reference, like that. And so you have to call, this is the constructor. It's just not automatic. You have to do everything by hand in C. So So do you guys see how it's pretty similar to C++? Malloc is these are the main differences. Malloc is used instead of new. Make sure you call the constructors. It is more verbose. The fact that it is explicit, a lot of people like it, right? There's no secret function running, But if you forget, you're toast. But when you're a C programmer, you kind of get into these habit of you make an object and you call an init on it, and there's no performance difference between that and C++ because C++ just inserts that init for you. Okay. And then we should be done at that point, I think. So we can return. Otherwise, head and tail are set. So then we are going to make a new one. So list pointer new dude is equal to list pointer malloc size of list. Make a new node, and again we have to call init on it. Node init, passing in just passing in. Yeah, that's a pointer. Passing in new node like that. It's already a pointer. We don't need to pass it by reference, right? Because new node takes in a node pointer. So we're just passing in a node pointer. Should probably compile this and make sure that I didn't screw anything up. New node is undeclared. Yeah, new dude. Yeah, new node. There we go. Assignment to node pointer from incompatible type list pointer. Yes, thank you very, 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 very much. This should be a node pointer. That's why we do this casting, by the way. Do you see that? I created a list pointer instead of a node pointer. A node pointer is an element of a linked list. The list is the whole thing. And so when you do the casting like this, that created a type conflict. Without it, it would very happily cast from void pointer to node pointer. And it would be the wrong size. Actually, it would be the right size, because in this case, they're exactly the same number of bytes. It would actually work, and it would work silently, and that would be my bad, right? Because if I ever changed the node class or the list class, everything would break, and I would have no idea why. So it's always very important to do this. Let's say that I even did that intentionally to demonstrate this point to you guys, because I am that clever. So, yes, it was all intentional. It was a teachable moment. So. They believe me. You prefer C++ over it? Yeah, me too. Especially because data structures are really better in C++. I think it's kind of. Honestly, there's no difference when you get down to it. But I like encapsulation. I like having an interface, a public interface, and a private implementation. I like that separation of concerns. Like philosophically, like C++ makes more sense to me. I like constructors guaranteeing my code has initialized the variables. Okay. So, but I've done a lot of C programming too, and it doesn't bother me. Like, I like C. Okay, so let's push back. Okay, so we've created the new node. Now we need to hook it up, right? So we're coming in at the end of the linked list. So the old tail needs to point at the new dude. So tail points to lists tail points to. Remember, we don't have member functions, right? So we can't just say tail. This lists tail points to next equals new node. Attach the new dude to the bottom of the list, right? And list points to head should not change at all. List points to size needs to increase. We need to do that here as well. Keep track of the size. And we need the new dude's previous to be the old tail. So new node points to previous is equal to tail. And its next has already been set to null. So now we just need to move the tail down. So tail is equal to the new node, and we're done. Okay. So that looks very, very similar to C++ linked list code, with the exception of new being malloc, and not having member functions means you need a little extra typing. You have to pass the list in, every time. Am I forgetting anything? Doesn't new node have to be a node? Yes, thank you. Yep. Tail is undeclared. Best points of tail. Okay, so now in order to verify that this thing works right, we need to have a print list function. So let us write a function that will sneeze. Okay, so void print list, taking a list again by pointer, like that. And so when the enter is 0, if temp equals 0, we'll break out. Zero for done. And then when we're done, we will print the list. Print list, passing in the list again by reference, or reference to the list. Yeah. And yeah, sure. Or I could have made this list here a pointer and malloced it as well. But this is fine. So print list, list, pointer, list. Okay, so again, assert that list exists, right? For all these functions, you have to do this. This is not necessary in C++, because when you call a member, again, when you call a member function, you don't have to make sure the guy you're calling it on exists. Unless you did something really wonky, it's going to exist. Big bless you. Thank you. Thank you. All right. So list. Okay. So how do we print a linked list? All right. So for list pointer temp equals list, as long as temp is not null, temp equals temp points, not a list, 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 not a list. Node pointer temp equals list points to head. There we go. Temp is equal to temp points to next. All right, so what this is going to do, it's going to create a temporary pointer that's pointing at head. And then it's going to do the thing here where we're going to printf, we'll just print the number, I guess. Temps data. No privacy, no get, no getters, no setters. You could write them, but it's all, it's all public, right? So yeah, maybe I should write a getter or setter. Okay. Because you can. There's no enforcement of that at the language level. You could just make a get and a set and just tell people to call it. Right? Okay, so we're going to print temp data, and then that's it. Okay, so we start off, we make a pointer to the top of the list. Is the top of the list valid? If head is null, it quits immediately. Otherwise, it will print the value of head, and then it will move to the next element in the linked list. check to see if that element is null. If it's not null, then it prints it. Moves on to the next one, check to see if it's null. If it's not null, it prints it, so on and so forth. So, moment of truth, 42, 52, 10, 0, and it printed nothing. Maybe I should set the data. What do you guys think? That would be cool, right? That would be neat. So node init must now take a data. And if you're like, well, could you have one version where it takes data and one version where it doesn't? You can do that maybe? Does that work? I don't think it works. Yeah, it doesn't. In C, every function has to be a unique name, right? We learned this from assembly, right? So if you want to have one version that takes in data and one version that doesn't, you would have like node init and node init 2. And so node init 2, you can pass in the data. Node init, it default constructs it. So we will do node init 2 passing in data. 42, 52, 32, whatever, 0. And there we go. Didn't get 42. Interesting. 10, 20, 30. 0, 20, 30. Interesting. Oh, that's right. Because we didn't pass it in here either, right? That's what happens when you don't have node init. Node init 2. You don't have a constructor. Okay. 10, 20, 30. Done. 10, 20, 30. There we go. Now we got a fully functioning linked list class in, not fully functioning, but functioning, right? Now we can add push front, pop back, pop front, blah, 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 insert in the middle, delete in the middle, search, all that kind of stuff. But it basically works out the same way. Rather than having a member function, you have to pass in the list itself, right? And so that kind of will give you an extra level of indirection and everything. In C++, it kind of works the same way, except it's explicit, or it's implicit, right? So you would just say tail equals tail points to next or something like that, right? And what that means is this points to tail is equal to this points to tail points to next, right? In C++, it generates the this points to for you, and that's effectively the same thing as what we have going on here. Every time you have a member function call in C++, it actually passes in a pointer to you invisibly. So all of these things we have that are passing in the list, the way a member function works is it actually just passes it invisibly in this. And if you refer to something just like tail, C++ will actually insert for you this points to for you. And so you could write code that just looks like this instead. Tail equals, and you could write this. You write tail equals this points to tail points to next in C++. This is C++, not C. Right? So, yeah, that's how a member function actually works behind the scenes. It actually passes. It's just a function call. It's just a function call. There's nothing magic about it. It's just a function call, but it passes in a pointer to you behind the scenes, and every time you refer to just tail unqualified, it says list. This points to tail for you. So it allows you to eliminate that parameter, having to type it. Yes, thank you. That should be a size of a node. Thank you very much. Okay, an aesthetic analyzer would find that, but yeah, that's one of the reasons why new is nice, rather than that, which was a very serious bug actually, because if you partially allocate a struct, that's really, really bad, where some of the thing is actually allocated, some of it's not. That's a serious problem. In C++, you would just be like head equals new node, like that. there's no opportunity for you to screw up. You know what I mean? Like, I mean, there's plenty of opportunities elsewhere, but like in this case, the type checking is strict. You'll do strict type checking. If I tried setting head to be a new list, and again, this is C++, not C. If I try doing this in C++, it would not compile, right? Whereas this code compiles just fine. Like if you leave off the type def, and so you can have situations like that where you type in the wrong type. And right now, it would actually be fine because the size of a node and the size of a list are exactly the same. But then later on, if I change it, then it will break, and break horribly. So, so C++'s system is more dummy-proof. You hope assembly linked lists are not as difficult as this. No, we're not going to be doing assembly linked lists. We're going to be doing bridges assembly linked lists. Okay, so so what does this look like? I just want to see if there's anything else I need to talk about from the C perspective. One thing you can do is you can do what's called calloc, like the cereal company almost. Calloc will allocate the memory and zero it, and that way you don't need to call the init functions. At least the init functions that set everything to 0. Calloc will do that for you. What else matters? Something I was going to talk about. I don't know. Printf, Scanf. Oh yeah, strings, right? All right. Strings in C are the worst part of the language. They're 100% garbage. They come from a time period when not wanting to keep track of the size actually mattered from a space perspective, from a RAM perspective. I don't know if I want to get into strings today. I really don't. I really kind of don't. Like, we spent an entire semester studying how to do them. We've kind of talked about them before, right? It's a null terminated. You guys did a homework assignment on it. Just gonna ignore them for now. Okay. So let's see how, because I want to get into how this looks in assembly. Okay, so what is a class in assembly? What is a class in assembly? A class in assembly is an array. That's it. So you guys already know how to access a class in assembly because you know how to do arrays. What's different about a class in assembly is that each element of the array could have a different size, right? In this case, they all have the same size, but I could make one that's not, right? So let me just put this up in the public directory. So move ll.c to /public and make the world public. And so if you guys want to look at my beautiful source code, this is found in /public/ll.c. So that is my beautiful, beautiful linked list implementation. And so let's talk about what classes really are, because there's a lot of sort of illusion and deception that takes place in C++. Like I said, every time you have a member function is just a function. But because of name mangling, you can't just call the function directly, right? You have to call it on an object, right? So if you're in main.cc and we do something like class Bob, and Bob has, let's make it a struct for simplicity, and Bob has a member function called print, and it'll be like I am Bob, right? Doesn't really matter. probably put a C out there, huh? C out, I am Bob. Okay. So what is going on? Do I need this code? I think I preserved it already, didn't I? Go away. All right. So int main. It's pretty funny. So if I say Bob Muya, and I say Muya.print, voids, voids. I am Bob. Okay. So what is going on here when we have this? What is actually happening behind the scenes? What is dot print? Right. So let's compile this G++ dash capital S optimizer turned on main.cc, and let's look at main.s. Okay. So what is going on here? You might actually optimize all of that away. Yeah, it inlined it. Fine, let's not optimize it. I'm Bob. Okay, so you can see that we have a function called zin3 bob 5 print ev, right? So this is name mingling, right? So do you guys remember how we talked about name mingling? How like C++ functions will get name mingled? It actually generates a function in the global namespace named _zn3 bob 5 print capital E lowercase v for us, and so that means this is Bob's print function, basically. And there's no real way of calling that by accident. You know what I mean? Like, you know, you can't make a function named that. I don't believe. I think underscore is reserved by compiler generated stuff, so you can't actually generate something with that name. And then here is Bob's print function. And so Bob's print function begins here, pushes some variables, messes with a stack pointer, loads probably the string L33, probably the string, word LC1. LC1 is I am Bob. Yep. Okay. So it loads I am Bob, and it loads I am Bob plus 4 into R0, and then it calls branch with link into cout. So that is what cout looks like under the hood. It is gargantuanly ugly as a function name. And so it puts, it loads I'm Bob, calls cout, does a no opt for some reason. No opt means do nothing. I don't know what that's about. And then it returns. So that is what's going on here. So what is this thing here, right? So this thing here is cout. Okay. So it's actually passing in cout as the first parameter, and it's passing in I am Bob as the second parameter. That's because the double left arrow operator takes two parameters. It takes in cout and it takes in a string. And so it takes cout as the first parameter, right here, right? L33 plus 4. L33 plus 4, right here. Word, 4 bytes. So it's taking cout as the first parameter, and it's taking I am Bob as the second parameter. And then it calls this function here. This is actually the double left arrow operator, essentially. Okay. So, yeah. And so, if we were to do something like this, main.cc, int score void score to 0. So score gets added to it. So and then we could print it or something. My score is score. What does minus equals minus mean? It's minus equaling minus add. So it's adding add to it. It is the meme way of adding a number to each other. So we've got Muya here, and we're going to say Muya scored a touchdown, so add score 7 points, and then actually 6 points, and then we'll get the extra point, and we'll say print. Yep. So score 7, good. The code works. Let's see what's happening behind the scenes here. EU4 is a group assignment. That is correct. It is a partnered assignment, not a group assignment. Are they working in groups or are they working in partners? It's a pretty big difference. All right. So section text, add score. Is EU4 one of our assignments? That's for CSI 41 right now. Okay, so here is Bob's add score function. Okay, here's Bob's add score function, and args 0 frame needed 1 store load add load store no op for some reason. A lot of frame pointer math. Load frame pointer stack pointer return. Interesting. What's actually going on here? Oh, I see. So that's the actual thing here. So R2 is the current score, and R3 is the new score. And then we store the new thing back. Okay. Okay, so let's see here. So R0 is probably going to be Bob. Like I said, there's a secret pointer that's passed in. I don't think we do anything with it. That is going to be... We don't do anything with that either, so both of these things are basically pointless. No, we do load from it. Okay. So we're storing R0 into this memory address, and then we're going to load it later. And so that's the location of, what was it, Bob, I guess. That's Bob, or Muya in this case. And so we're writing the memory address of Muya into frame pointer -8. So remember, the stack pointer goes down like that. Stack pointer's at the bottom, frame pointer's at the top of the current frame. I don't know if we talked about that before. Yeah, with linked list. So when you have your stack like this, if you have a function f that calls a function g, which calls a function h, what happens is that the stack goes down. All of your variables live in these different stack frames, and they coexist happily with each other. What happens when we call h? Well, first of all, C++ figures out how big h needs to be. Like if you've got an array, like if somewhere within h you've got like int array 100, then it will move the stack down big enough to hold array, which is like 400 bytes, right? And then there's a couple other things that go on there, like the return address and things like that also go on there. And so what happens is the stack pointer moves down to here, but it's very useful to know where the top of the frame is as well. And so this is called the frame pointer here. Frame pointer is the top of the frame, stack frame, and the stack pointer is pointing to the bottom. And so, or vice versa, I always get them mixed up. Yeah, so the frame pointer is, no, it's the other way around. Moves down, let's see, add, subtract, stack pointer moves down. And so the frame pointer, yes, the frame pointer is the top. So the frame pointer -8. So we put the address of Bob into the frame pointer -8. We put, what would that be? Add the amount we're going to add? Or is that's probably an address also. Yeah. Or maybe that's the value to add. I'd have to look at it. Into frame pointer -12. And so you'd have in here Bob like around here, and you'd have like the amount to add in here somewhere. And so they're indexed by like talking about like frame pointer -4, frame pointer -8, things like that. You don't need to do this when doing assembly, but oftentimes it's nice to know where the top of your stack frame is, and then when you move the stack pointer down to make room for variables, you need to know where the bottom of your stack is, you need to know where the top of your stack is. And we haven't done any of this yet because we've been able to do everything in registers so far. Do you mind going into exactly what a frame is? Yeah. So does that make sense, Muya? So this is called a stack frame. So that is a stack frame, and it holds all the variables for the current function. And then if one function calls another function, then that's another stack frame. And our current one, all the local variables you have are in it. So this is what you do when you need to deal with more variables and you have registers. Yes, exactly. The compiler, though, is just being dumb, right? And so the compiler generates, with the optimizer turned off, the compiler generates bone dead, like just stupid, like ignoramus, level assembly code. None of this needs to take place. All of these loads, all of these stores, they're 90% of them are redundant. And the reason why it does this is it generates poor code to begin with that is correct, that it doesn't have to worry about running out of registers and things like that. You'll see over and over again, it's like loading from, so it stores from R0 into frame pointer -8, and then it loads from frame pointer -8 into R3. It could have just moved R0 into R3. You guys know what I'm saying? Like you could just have done a move from here into here, right? And then again, it uses R3 again, and so it loads from R3 into R2, and then immediately overwrites R3 with frame pointer -12, adds those together, then it loads into R3 again, and then it stores into R3. And so it keeps using the same registers over and over again. And this is so that it can generate correct assembly without needing to worry about like register allocation and things like that. Then what happens is the optimizer comes in and fixes it, which is why you should pretty much always have the optimizer turned on your code, because all this nonsense here is just bad. All these loads and stores, loads and stores are way slower than register, right? Even if you get an L1 cache, you're still talking, there's a 4-cycle delay on these things. So this is really slow code. And if you just even turn on the optimizer at level 1, the reason why I didn't turn it on was because I didn't want it to get inlined, which is a legitimate concern. So let's see if we can find it. Add. call this my print. Yeah, it's getting optimized away, right? So that's the problem with trying to use the the generated code, is because I wish there was an intermediate step where it just would not. There's options you can pass in on that, but it doesn't matter. So my print, okay, that's actually not what I was looking for. It was add, wasn't it? Add score. Branch of link. So put 6 points here, branches with link, adds 1 point here, branches with link. And anyhow, so the point is that the class gets passed in as a secret first parameter. So when you've got a function like this, there's secretly, it's just a function called mangle bob add score mangle, and it's going to pass in muya as the first parameter. When you do this, when you say muya.myPrint, it passes in muya as the first parameter and then add as the second parameter. And so the functions, if this was in C, it would look like this. It'd be like garbage, add score, garbage, bob, pointer, b, and add. This is technically what the function looks like, right? And so the function, add score function, is just this garbage name mangled thing like this. Not quite that long, something, whatever. But it passes in a pointer as the first parameter, and that pointer is muya. Okay, so this here is actually just some syntactic sugar over calling a function, passing in muya as the first parameter. Okay, that's all a member function is. You guys understand? Does that make sense? So when you say variable dot something, it actually just passes in that variable as the first parameter to a global function, that you just don't see normally. You guys still think? And so let's see what we can do here. So let's have a score. And let's have an age, and the age, let's make it a double. And default to 32.1. And let's have a string that's called name is equal to Bob by default. And let's have a char for the team. You're going to be on team A by default instead of team B. And just going to delete all these member functions and let's call this sports ball. Okay. So Muya's score is 42. His age is negative 16.122. Okay. His age is 420.21. Absolutely no way of doing this without insulting him. So we'll just go ridiculous. He'll be 100.1 years old. Name is Nick, and the team is going to be Team B. Okay, so So then we can do things like this, right? Cout is age is certainly age that. Okay, so and we can do that for all the different things. Now, our topic for today is classes, right? And how classes work in C was the first half of the lecture. Now we're going to see how they work in assembly, so that you can do linked lists and bridges. So, so how does this in assembly bridges? Yeah, yeah. So let's make a function called extern C. We'll just do the add score function, right? Add score. It takes in a sports ball by reference, by pointer. Let's just do by pointer. It's the same thing, really. Named S and int new score. So we want to write a assembly function that, given a sports ball pointer, we add whatever number we pass in here to the score. Okay. We're going to add 7 points. Okay, so do you guys understand what we're doing here? So we're passing a pointer to an assembly function, and we want the assembly function to pick out just that, right? You guys understand? Do you get what the assignment is? Doing classes. Cool. Before we do that, though, let's see what memory address all this stuff is at. So cout so what address is Nick at? It's a variable, right? And then the address of muya.score. Age, name, and team. So do you see why I'm doing this, for one thing? I'm actually going to be outputting the memory address of the variable for Muya, the variable for Muya.score, the variable for Muya.age. So it's not because the actual addresses in RAM interest me, but because I'm curious how it's laid out in memory. Which order do they come in? Because I need to know this in order to tie my assembly code to it. Okay? What do you guys think? Do you understand what I'm doing? Why I'm doing it? If I'm going to be messing with these memory addresses in assembly, I need to know where they are first, right? I'm going to be passing a base, and then I need to know what the offset is. What is the offset to score? What is the offset to age? What is the offset to name? What is the offset to team? Okay. So let's find out. Error expected constructor. Yes. Okay, so he's at that memory address. Score is at the same memory address. So what is the offset for score? We haven't learned hex yet, have we? So we can do this. Yeah, so the offset is 0. Okay. Now for age, let's see if this will work. Invalid. See if I can coerce C++ into telling us just what the offset is. No, it doesn't like it. All right. All right. Well, let's learn hex real fast. All right, so hex. Let's not learn hex real fast. I'll just do the math for you. So E is 16 bytes higher than D, but it's 8 bytes lower. So age is 8 bytes past score. So age's offset is +8. You would think it was +4 because score is 4 bytes. So you'd think that the next one would come in at 12, but it's not. It's coming in at 16 bytes later. And the reason for that is because doubles are 16 bytes, and so they are on a 16 byte aligned boundary. Name is coming in 8 bytes after age. You see that? Which makes sense. Age is 8 bytes. And so having name coming in 8 bytes later makes sense. And then B? Maybe, Why did it just print B? B. Why is it printing B? What did I do wrong here? The memory address of the team variable is B. All right, that's a little strange. I have no idea what memory address B is, dude. All right, so here. Okay. That's weird. All right, so here we go. So here, I just converted it to an unsigned integer for you guys, so you don't need to know hex. So that's the RAM address that the chunk of memory starts at. And remember, an object is just a integer. It's just a place where it's the base. It's the base memory. And then the offset of score is 0. The offset of age is 8 past the beginning of the block. Name is 8 past that, and then team is quite a bit past that. So it's 24 bytes past it. And that's because the string actually has a couple things under the hood. It's got a pointer to the beginning and a pointer to the end, and maybe a size variable in there, something like that. So we just learned that strings are 24 bytes, and it might actually, in this case, be the entire string. There's something called the small string optimization, where it will sometimes just not have all the rigmarole of a whole string. It'll just be literally an array of 4 bytes and some spaghetti on top. Okay, so we are not using 64-bit ints. This is a 32-bit int. Now watch what happens if I change these things around. Let's see. What if I make them all ints? You see how each one is 4 bytes past the one prior to it? 32, 36, 40, 44. I can line this up for you. I can even do this. And now I can get the offset. Yeah. So I'm just going to subtract the memory address of the base. Damn it. Ampersand, thank you. There we go. So that's the base. That's the memory address. Score is at offset 0, age is at offset 4, name is at offset 8, team is at offset 12. And so if you were to do this in assembly, you would load from, like, let's say you wanted to load age. We're going to load into register 8 from register 0, which is your base that's passed in, plus, which one did I say? Age or name? Which one did I say? It doesn't matter. Let's say we're going to load team. Then we're going to add 12. Okay, so this would be how you would load muya.team into register 8. The base is passed in as register 0, and then you select the team by going to offset 12. You select the name by offset 8, age by offset 4, score by offset 0. Does that make sense to you guys? It's just an array. And if they're all ints, it's actually literally just like an array. But classes are LDRB. No, this is an integer. So it is LDR. Classes are just arrays. And in this case, it's literally the same thing as if I had passed in an array of integers. Like the code wouldn't... Like if I called this assembly function passing in an integer array, it wouldn't know whether or not we were dealing with a sports ball or if we were dealing with an integer array. It's just an array of 4 integers. It's literally the same thing under the hood. Now, what makes no, it's fine. Yeah, getting LDR and LDRB is something that I you saw me do it live, right? So it has nothing to do with the information being passed in. It only has to do with how it's declared. So how the class is laid out in memory is something defined by the C++ standard. So in assembly, you have to know how the thing getting passed in is laid out in memory. And so you do something like this, right? Where you basically just say, okay, here's all the elements, and as you hope that somebody doesn't come in later and like screw with it. Like, I want to alphabetize these things, and they come in here like this, and they're like, all right, H, and then let's see, S is after that, and it's before T. There we go. It's nice and alphabetized now, And then all of a sudden, all your code breaks because the offsets are all different now, right? And so in C++, the way that you declare, the order that they are declared in the class is actually the way that the memory offsets are set. So by looking at a class definition, you can actually tell where the memory offsets are going to be. Like I don't actually need to go through this rigmarole for simple classes like this. It gets complicated though when you start doing things like strings and you don't know exactly how big a string is, right? And so it's a good idea to do this when you're doing a sort of complicated class. But basically, by just looking at this, I'm like, all right, that's going to be offset 0. No, you're not 0 by right. 0 offset. You know, this guy is now 4 offset, 12 offset. Are you guys with me on this? Like, does that make sense? The order they're declared in the class is the order they're laid out in memory. And so there's been some proposals on having more control over that. There's also some weird syntax that I never really use where you can control these things. It's like :8, something like that. Let's see if that works. No. Yeah, there's a way that you can actually specify what the memory alignment is of elements in these things. I don't remember off the top of my head how to do it because I never use it. Maybe like that. It's a bit field. Yeah, I never use it. Okay, so what if we have a heterogeneous class though, where heterogeneous means not everything's in it. Right now, this is exactly the same. Like I could actually just make an integer array named Muya of size 4 and set it equal to 42, 100, 5, and 2. And this would actually, you could, if you pass that to this function, it would work literally the same way as this class right here. Like this to assembly is exactly the same as this. Do you guys understand? Like, now it gets tricky though when you have a heterogeneous array, which means you got elements of different types. You got a string in here, you got string name, and then you've got a double for score, and what was that? It was supposed to be an int score, double age, char team, so Nick is now 42.1 years old. There's Nick. And should score 5, and the team will be B again. Now, you will, yeah, all these things are going to be wrong now, right? This will still be 0 offset, so cool. But now let's find out what the offset is for these things. So this is a heterogeneous array. It's basically, all a class is an array with different types for each element. That's really all it is. Behind the scenes, it's literally just an array. Okay. So if we compile this and run it, hopefully this is interesting for you guys, right? Score, let's put these in the order they're in the class now. So score is down here, so it goes age, name, score, team. Okay. Do you guys find this interesting? Because like you're going to need to know it. Like we hide these details from you when you're learning C++, but now that you're in assembly world, like you actually get to see how the world actually works, right? Every time you have a member function, there's secretly a pointer to this passed in. When you have a class, all it is just an array, you know, and C++ will keep track of these offsets for you, and so it'll just be like load from memory address plus 32, yeah, g++ -s main.cc, then main.cc, main.s, sorry, right, and so that's probably going to be loading the thing at memory address plus 32. Right. See that? 32, 36, 32, 36, right? So these are the offsets, and C++ just computes them. Right? And then it's going to, you know, you preferred when it was magic? Would it be a strat to always do strings last in a class so you don't have to worry about offsets? So Yeah, so some people actually will worry about the memory usage of their classes, and and the thing is, yeah, how you lay out your class in memory can make a difference, because you can actually have wasted spots in memory. If you have an int followed by a double, you've actually wasted 4 bytes of space, because doubles have to be aligned to 8-byte boundaries, ints are aligned on 4-byte boundaries. So if you go int, double, you're actually wasting space. And if you go int, double, you've actually wasted 8 bytes of space. So rather than your class taking up 24 bytes, it's going to take up 32 bytes. And so, yeah, so these kinds of things matter, especially in embedded systems. Yeah. For systems that have 32 gigs of RAM, maybe not so much. I don't know. So the offsets here are 0, 8, 32, 36. Okay, so 0, 8, 32, 36. So you can see that here, a double takes up 8 bytes, and so the next person starts 8 bytes later, and the string takes up 24 bytes, and so score starts 24 bytes later. It doesn't waste any space because it could be aligned on a 4-byte boundary, so that's cool. What if we move score and team around? Okay, let's try that. So chars are aligned on what boundary? What do you guys think? So group up your types. Yeah, if you care. If you care. So this guy will probably be also at 32, right? Because the string is 24 bytes, so char will start at 32. Do you think that int will start at 33? Char is only 1 byte, right? So do you think that score is going to start at 33? What do you think? You guys are correct. 36 is the right answer. So, so there are 3 bytes of wasted memory in this class. And if you care about 3 bytes, which you do, I'm being a little bit sarcastic. If you're on a modern PC, I would not give a rat's ass about this. If you're on an embedded system where you've got like a K of RAM, then yeah, I would definitely pay attention to how I do this. Yeah, score cannot be on 33. That is correct. Will the optimizer change things? What do you guys think? Anyone want to place a bet? Double or nothing? You're great in the class? I'm kidding. All right, so read is double or nothing. All right. I'm kidding. Bump me up to a 220%. All right, here we go. Let's run it. Diamond hands. Nope, didn't change anything. What if we did this? Maybe the optimizer can put the 2 chars together. What do you think? No. Right. It's because the order they're laid out. I seem to recall actually the optimizer messing with padding before, when it pads the number of bytes out like this. But in general, in the order that you lay out your variables is the order they're going to be in memory, and that's if your thing changed based on the optimizer settings, you wouldn't be able to know. Like if you were to pass a sports ball to a class, you wouldn't know, or to a function, you wouldn't know what the offset was supposed to be, right? So these things need to actually be fixed. And now if I were to move this up here, then you see it is indeed at 33, right? Because chars can be aligned to 1 byte boundaries. And if I were to move team 2 up here, and I'll have conversion. What the hell? Oh, it's yeah, it's because of the constructor here. Okay, so you can see that age is 0, team 2. So you see that team 2 is 8 bytes after CNIC. Team 2 is 8 bytes after the double, and now the string has to be aligned because it's a 32-bit pointer. The string gets bumped to byte 12. The char then appears 24 bytes after that, and then the int takes 4 bytes after that. So the upshot here is these offsets are what you use in assembly. So if you wanted to load team, it would be LDR. Let's load into register 10, and we're going to load from register 0. Register 0 is Muya plus 36, right? And so that will give you team. And in fact, this would be Nick before was like, shouldn't it be LDRB? And this one should be LDRB because team is a char, right? Char is LDRB. Okay. So do you guys understand the assembly for this? So that's how you pull member variables out of a class that gets passed in. Okay. So that's about it for today. I guess no homework. We didn't get quite to the homework yet, but it's all right. You guys get a couple days off, I guess. Man, that's rough. Oh, such is life. So no homework for now, I guess. Enjoy your weekend of 2 days before the next homework's time. But this is a pretty important thing to understand because, as you can see, when you understand assembly and you understand what's going on here, you might actually design your class differently, right? You might put the chars together, you might put the ints together, and things like that, so that you don't waste space. And if you're on a memory limited system, like an Arduino or something like that, like doing this kind of stuff would actually probably make a big difference, right? And, if you've got a K of RAM, or if you're making a vector with like 10 trillion elements in it, then yeah, things like this will add up. It'll also matter for caching, maybe, depending on how big your class is and stuff like that. So just kind of understanding what's happening behind the scenes, kind of pulling the blanket away, will make you a better C++ programmer, even if you don't use this assembly directly in your professional careers. Can chars be used to fill in the spaces of free bytes? Sure, yeah, why not? If you had a 4 byte gap between a double and an int or whatever, yeah, put chars in there and it's free memory, essentially. It's just free real estate. Yep. You understand assembly, you understand life. You understand assembly, yeah, you know what your machine's actually doing. Because these are the actual commands being run by your CPU. Yeah. So, okay. That is it for today, guys. I will see you guys on Thursday, and have fun playing Valheim or whatever.